So Unit 13 is on a topic called mechanical properties of materials. So in a loose way, we'll just say that we're talking about bulk quantities and also just overall effects that materials have to forces and other inputs. So there's about, I don't know, maybe three key formulas here. I could give you lots of formulas here, but I've tried to put it in a way that it's digestible for a 2 to 3 hour class, which is what we have usually is a 2 to 3 hour class in terms of like just straight up like lecturing and calculations, and of course supplemented by questions and answers. The first idea that we're going to cover is this topic called stress. So I'll give you a proper definition of what stress is, and then we're going to shift over into another topic, which is called strain. And finally, we're going to talk about elasticity. After that, I'm going to start talking about design a little bit. And what I mean design, I mean like very basic stuff. So by the end of this class, in theory, and I guess in practice, by the end of this class, you could go to your, I don't know, your garage or your shed or your toolbox, and you can grab a piece of wire or whatever, a material, let's say it's just a copper wire or something, and you can measure the diameter of the wire and you can estimate how much of a load or a mass, if you want, this wire could hold if you were to lift something with it. Like, so we're starting to identify um, based on the material what it can handle in terms of its performance when it undergoes or is carrying forces through it. So speaking of carrying forces through it, we're going to talk about the first item on the list here, which is stress. So what is stress? So the mathematical definition is right here. Oh, and by the way, the mathematics for this unit is very easy. You're just using basic operations. Think of bed mass. If you're good at bed mass, that's all the math you need for this chapter. The little nuances come in effect when you're talking about unit conversions and the metric system and the imperial system. That's where it gets a little bit dicey, and you got to be a little bit careful with what the heck's going on there. So here is the idea, or the formula, I should say, for stress. So stress is given this Greek letter sigma. It looks like that. You can look like a whistle or something. And then that is equal to a force and per unit area. So an example of stress would be like this. Anybody know what this is? What does this mean? 4 psi. What does 4 psi mean to you?
Pounds per square inch.
Thank you, Victor. Yeah, pounds per square inch. So there's 4 pounds applied to 1 square inch. Okay. Sorry, my fun times with the stylus here. There you go. So ask yourself, put your thumb, if you have your thumb handy to put on the table there. Imagine that you put a 4 pound mass on it, because my thumb, I'm looking at it, the area of my thumb, just the tip of my thumb, like where the nail is about a square inch. So if you put your thumb on the table and you had 4 pounds of mass on top of it, do you think that would hurt you? Would that feel like a little bit painful? 4 pounds?
No, it should be okay.
Yeah, most people would probably say it's okay, but obviously everybody's threshold is different. Well, the idea is that where you apply the 4 pounds of force, depending on the area that it's on, could profoundly affect your perception of how much you can handle. For example, if I were to lie down and take a 50-pound dumbbell and put it on my chest, I'd probably be okay with it. I mean, if you've ever done like wrestling class back in high school or play a little sports, a 50-pound jolt is not going to like do too much damage to most people. But if you took a 50-pound mass, I say 50-pound mass or weight interchangeably. We talked last time about pounds, how they can be interpreted as mass or weight. If you took a 50-pound mass and you put it on the fingertip, do you think that would hurt? Please don't do that. Do not experiment. Yeah. I don't want to have any students emailing me after and saying, "Sir, I have a finger injury because I put a mass on my finger." I'm just obviously joking. But yeah, if you put a 50-pound mass on your fingertip, it's probably going to be very painful, and you probably should not do that. You definitely shouldn't do it. So the idea of how much the material, in other words, your finger, can handle, really depends on what the area that that force acts on, and also how much force you have. So that's what this is. Stress is telling you that. Stress says that if you have a lot of force, you're going to have a lot of air, a lot of stress. And for the area, if you reduce the area, that's bad because then the stress goes up. So we we uh we know that materials will undergo stress, and it's been carefully documented how much stress materials can withstand before their integrity to resist forces and stresses is diminished. In the metric system, there are the following units, and you need to have these in your brain programmed, okay? We're not going to talk about too much unit conversions, but in the metric system, the units for stress are megapascals. And then the base units are newtons and millimeters squared. So you might wonder, why the heck would the base area be millimeters squared when I've been preaching to you all year that you should stay with meters because meters are the most orthodox of units in the metric system. The reasoning is if you look at 1 meter squared, if we're talking about the cross section of a beam or something, and you were to write it in square meters, um, it's it's a very large area. So if we're talking about a cross section of a wire or a cable, you're more likely to say it in square millimeters or even square centimeters sometimes, because that you want an answer that hopefully has a whole that can be represented as a whole number instead of just as a fraction or something really small. The other reason is most most stress values for materials that are used in construction are in the domain of megapascals or possibly G or gigapascals. So because of that, megapascals corresponds nicely with millimeters squared. The reasoning is that 1 millimeter squared is very small, but if you had 1,000,000 millimeters squared, and you can do this calculation on your own, 1,000,000 millimeters squared is exactly 1 square meter. So that's where this factor mega comes from. Remember mega over here, this mega m here, it literally is shorthand for 10 to the 6. So that's a few things to discuss there. In the imperial system, we have the base unit, which is PSI, and as I've clearly said over here, and in its name PSI, the abbreviation, sorry, the acronym clarifies that it's pounds per square inch. So those are the units for stress. You need to have these, you don't have to have them memorized, obviously, because we're not going to be testing you in a closed book fashion, but you will have an assignment. So what you can do here is you can draw a triangle if you're just doing calculations later or just for the future. You can say here, let's for example, we'll have here force and then stress and then area. Let me know in the chat, have you ever seen a triangle thing like this before to help you remember a formula? Okay, thank you, Jai. And also, if you want, you can draw two triangles here. Let's see here. You can draw two triangles here and do it with metric or imperial. So this is the formula. These are just units. So let me just say here units. So this would be newtons, and then you'd have megapascal. I'm totally squeezing that in there. And millimeters squared. You can do a much better job of writing that. Obviously, this is not the most fun way to write for me. PSI, inches squared. Okay, so that really boils down to just one formula, and this formula will require the most discussion, so hopefully it's nothing too dangerous. There's only 20 questions today, and I think that we'll probably breeze right through them. So think of this as a lighter day compared to what we did last time. So let's take a look at the first example here, and it's pretty much just what I was showing you with that triangle there in purple. So we'll just zoom in that triangle. Hopefully it's still visible a little bit. So the question is just to complete the table. So let's help me fill in these boxes. This is actually a little bit of repetition. So what's the metric units for stress? The ones that I want you to adopt, or the ones that are most likely adopted in practice? Thank you, Sean. Megapascal. And what are the metric units for the force? What goes here? Newtons. And if we're using this, thank you, Victor. And if we use megapascal and newtons, then the base area normally would be meters squared. But because we're using megapascal, the base unit for stress, I'm going to stick with millimeters squared. In the imperial system, the formula is the units for stress are psi. What are the units for force? Good. Who remembers last semester the second unit where I made you mess around with a bunch of formulas? Remember that booklet with all the formulas in it from physics? And I just said, here's a bunch of formulas for your entertainment and your enrichment. If you go back, I'm talking about Unit 2. If you go back to Unit 2, you'll see that we did a table just like this. And I said to you it was more of a, didn't cover it in class too much detail because we're covering it now, but I said that we would revisit it. Okay, one last thing is, of course, rewrite the formula here. So if you want the force, you can use the triangle shortcut that I showed you earlier, or you can just do it in your head. This stuff here should be child's play for everybody here because you are rock stars when it comes to algebra. I've seen that on your evaluations. So anyway, there's force over stress. So now it's your turn to shine. You'll see that the math really is not that hard, but we're not going to just breeze right through this. I'll take our time. We're going to do 8 questions. So there's 8 questions using this formula. And that should carry us over probably to the first break, possibly. We'll see how it goes. Like I said, this is my first iteration teaching this unit, so I'm not in a predefined mindset that we have to do a certain number of questions in a certain amount of time. So here we go. Number 2. So a force of 200 newtons is applied to a wire with a cross-sectional area of 7 square millimeters. Now, 7 square millimeters is not that large of a cross-section, but we're not here to like critique how much cross-section it is. We're just here to do calculations. Well, the critique part about like, is it a good idea to or whatever, we're going to discuss the design perspective a little bit as we get toward the last questions where we have you'll see a nice couple of application questions at the end. So in this case, which unit system? Is this metric or imperial? Is this metric or imperial? Let me know in the chat. Thank you, Anthony. Okay, so we're going to use these units here. So what are the units for stress going to be? What are those stress units going to be? Um, so what are the units for stress? Stress in the metric system will have units of megapascals. Yeah, when you type it in, guys, thank you very much. Make sure that the P is capitalized. I'm not trying to pick on you. I appreciate it. It's capital P, okay? Because it's Pascal, like it's named after a physicist. So we want to show them some respect. So I'm just going to be copying and pasting from my quick solutions because as you can see, Anthony, hilarious. You're hilarious. I'll tell you some stories sometime, but maybe during the break. Anyway, there's been a couple times where I've created some crazy formulas, and then I show a colleague of mine, hey, look at this formula that I created. And then they pull out a book from like 1950, and it was in like a journal from 1950. And I'm like, oh, great. Someone else figured it out. Okay. Yeah. Anyway, here's the answer to this question. On just on a scale, no scales of difficulty. Just let me know in the chat. Was this easy to do? Let me know. Easy or not easy? Like, let me know. What did you think of this question? I got two easies. I got a thumbs. I got an easy. I got super easy. Okay, I'm scared of Amir now. Not really. Not really. Not really. We're good. We're good. We're buds. Okay. Okay. Jasikaran's on point. I like that. All right. So out of 25 people, including me, 7 people say it's cool. What about the other 18? Any those other 18 people there? Let me know. Some people hop in, not toss in some intelligence here. Christopher, thank you. Nikita, there we go. All right. Okay. Thank Mint, nice. Victor, I like that one. I just got some cards back from grading. So yeah, thankfully they showed up mint too. Uh, I used to say mint a lot. I honestly I used to say that all the time. Okay, question 3. A force of 200 tons. The reason that there's 8 questions here is because we're alternating between the metric and the imperial. It's kind of like double trouble. You gotta do the metric system and the imperial. I want to make sure that you're always, well well practiced in these examples. So in this case, we have 2 tons, and the cross section is 3.42 square inches. So we have a little bit of an issue because of tons. See tons? I don't see tons here. I see pounds. So can someone tell us in the chat there, what is 2 tons? Thank you, Anthony. Yeah, so 1 ton, TON, is imperial. And yeah, 1 ton is 2,000 pounds. So this is 4,000 pounds. So I've done these calculations earlier. I'm also, just keep in mind, everybody, this is my first iteration delivering this booklet. So if you find one of the numbers that I've typed up here is incorrect, let me know. Let me know for these easier ones, especially. Like for example, here, I'm going to 3 significant digits. So if you got like 1169 or something, keep in mind that I've rounded it to the nearest 3 significant digits. So you see the first step here is I just wrote down the quantities in their most basic form. And then we want to convert tons into pounds. As per Anthony's comment there, I just multiply by 2,000 to get 4,000 pounds. And now we literally have pounds per square inches, so PSI. Okay, let's keep on going here. In this question, we have 5,515 pounds, and it's being applied to a wire, through a wire, sorry. This time, though, we have a little bit of fun time because we don't have the area. We are given the diameter. If I give you a wire and I don't tell you that it's a circular cross section, please make the assumption that it is. But don't worry, I'm not going to play games. I'm just saying, like, most people would agree that when you look at a cross section of a wire or a cable, it usually is a circle or approximated by a circle. So we need to find that area. So the area requires a little bit of effort here. The area is pi r squared. So of course, my friends, you got to do a little bit of extra work here. So what's the radius of this wire? In the chat, let me know. What's the radius of the wire? Thank you, Jai. It's 0.25. Hey, don't fall into that trap. It's not. That's the diameter. So if you do that, I'm gonna leave it like that. I'm just gonna leave it like that. Okay. You'll see why, because I've already typed it. just a little bit more economical with my presentation here. So there's the answer. So this is just kind of like a side note. So you see here we have the force, which is 5,515 pounds, and there's the area, pi r squared. Notice that I put a quarter instead of 0.25. That's fine. And then if you put that all in your calculator, which I don't have any real concern about you doing, you're going to get 28,100 psi. Keep in mind, this is 3 significant digits. So it's 28,100 whatever. It could be 100 something, it could be less than 100, but when you round it, I want 3 sig figs. Can someone agree? Can someone confirm they agree with this number, this result? Thank you, Sean. I remember when I was creating this booklet, I was at I think it was up. This is before all the COVID stuff. I was up north somewhere, and I was like fishing. I was on a fishing trip or something. And I was like, oh, let me just code it. Let me code some chapter for my students. So I was fishing and coding. That's what I do. Fishing and coding. Anyway, are there any questions thus far? Do you feel cool with this? Like, what do you think? Still easy? Thanks, guys. So we're gonna keep on going here. We're gonna do 4 more and then we'll take a break. Most likely, I think. So let's take a look at this one now. We have a force that is applied to a rectangular, to a column that has a rectangular cross section. The cross section is 4.2 by 3.1 centimeters. And then it says determine the magnitude of the stress that the column experiences. So you're starting to see now like more of a practical design aspect to this. So here's the column. It's a rectangular cross section like that. But what you have is a force that's acting this way through the column. And this area is the cross-section area, which is that 4.2 by 3.1 centimeters respectively. The force is 85 kilonewtons, which we're just going to color the arrow with instead of retyping the number. So we have the goods here to play. So I'll do this one a little bit more careful because maybe, you know, some people want that extra little piece there. So the first thing I'll just write down is the stress formula. And then I'm going to backtrack. I'll backtrack now. And let's calculate the force. So the force is equal to 85 kilonewtons. What does the K stand for? Or what do we do with the K, people? What do we do with that K? Yeah, 1,000. Thank you, Jai. So that's 85,000 newtons. If you want to be pretty here, put a comma. That's fine. And then we need the area. The area is a rectangle this time, length times width. So that's going to be, now keep in mind, those are centimeters. We do not want centimeters. We want millimeters. So 42 millimeters, 31 millimeters. You're responsible to know how to do those conversions. I didn't do this calculation. So can someone give me that number, please? 1,200 something? Is it 1,200 something? Or is it 1,300 something? 1,302, can someone confirm? Thank you. The reason that you're wondering, I'm not doing times tables in my head because I'm trying to do 3 things at the same time. Usually I can multiply in my head, but that's not my real issue right now. I just want to get the right answer on the screen here. Okay, so the stress is equal to the force divided by the area, so 85,000 newtons, 1,302 millimeters squared. That gives us, I did this earlier and I got 65.3 megapascal. Can someone confirm? They agree with that? Thank you. So that's the answer, me just kind of walking you through it in the lecture. Let me show you the answer that I have in the solutions, which I'll post on Blackboard later today. I want to show you how I typed it up because I like to show you just I mean, what I've shown you here is very clean and economical, but that's just if you want to write it in one line of writing, just one line across like that. So anyway, you don't have to write it like this. That's pro level. Like that's just me trying to be cool and make it look pretty for a solution manual. Anyway, let's move on to the next one. So it says here that a concrete column with a circular cross section has a load of 120 tons. So that's the force. The force is 120 tons. So we have the force. Let's just write this down. The force is 120 tons. But we know that tons is equal to pounds, 2,000 pounds. So that's going to be 240. You double it and then put 3 zeros. Can someone confirm? That's not really a confirmation there. It's pretty easy. Sorry. And then it says that the stress is 2,100 psi. So the question is to find what here? We want the diameter and the cross-sectional area. So the first part is to find the cross-sectional area. What's the formula for cross-sectional area? If you don't know how to write the Greek letter in the chat, just use the letter S for sigma. Greek letter sigma stands for S, like it's pronounced as an S in Greek. So you can just write S for sigma in the chat. So what is the formula for area? F over S. Thank you so much. So that's going to equal 2,000. You see, when I'm setting up these questions, the first thing I'm doing is writing the units in the most orthodox way, like the way that makes them correlate very well to each other. And then I deal with all the other crap, like finding diameters and whatever later. So in this case, this is going to be 114.286 square inches to 3 significant digits. That's 114 square inches. So why did I do two approximations here? The reason is because I want to find the diameter later. So now we're going to use this number here to find the diameter, since that number is more accurate. So we got one answer out of the way. Let me just bold that or something here. Let's bold it and turn it red or something. There we go. So now we know that the area, is equal to pi r squared. You could also write it alternatively if you want, but that's fine. So in this case, the radius is equal to. Okay, I've already typed this up in the solution, so I'm just going to go with my personal answer there from earlier. At this point, you're just doing some semantics with the unit conversions. So there's the remaining part of the question. I'll give you time to document that on paper. So don't worry if you need a few extra minutes to do that. Absolutely no problem. So I rearranged the formula for the radius in terms of the area, and then I just plugged in the approximate answer here of 114.286. Got 6.03 inches. That's the radius. The question wants the diameter, so I doubled my answer here. So that's 12.06 inches. And then the question asks for nearest quarter of an inch. So I think that should be quick for you to figure out quarter of an inch. So it's either 12.25, 12.5, or 12.0. You just figure out which increment of 0.25 is closest to 12, which in this case it'd be 12 even. So that means that the diameter of this concrete column is exactly 1 foot. Oh, sorry, to the nearest quarter inch is 1 foot. So if I'm looking here, I'm on my condo, I got a column in my condo here. It's not a circular cross section, it's rectangular. But I do believe that the facade of it is rectangular, but the internal piece of it is potentially circular. And I'm guessing it's about a diameter of a foot, maybe a little bit more like 16 inches. So pretty realistic number. Anyway, of course, since I did design these questions while on vacation, so to speak, I try to put some sense into them to make sure they had realistic values, but don't take these as gospel for like real life design. We will be doing some design-oriented questions in the last part of today's class so that you can see real life numbers. But for now, we're just basically playing with formulas and ensuring the units are consistent. Example 7. I think we're good to go now. It says here, what is the kilonewtons of force required to generate 1.31 gigapascal? So that's even more than mega. That's 1,000 megapascals is a gigapascal. And the area is given in centimeters squared. So as far as you're concerned, we're going to call this like just it's a metric system, but the units are all screwed up, and you got to fix them because the units need to be in the more orthodox presentation. So let's go over here and just navigate through that. So the stress is equal to 1.31 gigapascal. How many megapascal? Let me know in the chat. How many megapascal? Yeah, so it's times 1,000. Thank you, Jai. So a gigapascal is worth 1,000 megapascal. That's 1310 megapascal. Okay. The area is a little bit messed up as well. We have 3.41 centimeters squared. How many millimeters squared is that? And don't worry, I'll walk you through this one. How many millimeters squared is that? Okay, so probably some people are rusty on this one. Remember that we have 10 millimeters for 1 centimeter. But because it's squared, you got to do it twice. You have to do it twice. So that's why the answer is equal to 341. And then from there, you're ready to rock and roll. You just take the formula for force. So I'll just use my solution. There. And that should wrap up that question. See, force is equal to stress times area. So there's the original, the OG. And then we have the units that are more orthodox for our calculations. The answer will automatically, because we're using megapascals and square millimeters, the answer will automatically be in newtons. But then the question wants us to take it a little bit further. They want the answer in kilonewtons, and we want 3 sig figs. So that's why this answer here is presented to you. So there you have it. A little bit of a quest, but just to take it back to the audience here, how do you feel about what I've done so far? Do you still think that we're sort of in the easy, or are you okay with this kind of stuff so far? How do you feel about these questions? Okay, thank you, Joshua. Thank you, Victor. Yeah, more steps, but still good. And that's good that you're saying that, people, because really it comes down to these two triangles. Not the formula, whatever, but it's these units here. This is the key. I don't care if you know the formula. If you understand the consistency between those units, then you are very good. Because if you get any units that deviate from these units here, then you just have to adapt. And also, you need to know the area of some basic shapes like circles and squares and rectangles. If you don't know the area of a circle, square, or a rectangle, then you need to figure that out soon, because you need to know that stuff. So let's do question 8, and then we'll probably take a break. Like I said, my first iteration teaching this example, so We've paced ourselves well. I had an idea in my head of how much it should be. So it says here, just read the question for a second. Sorry, I'll give you a moment to read that. Okay, so let's talk about the cross section here. We have columns. So if you're wondering the picture, what it looks like, there's a structure here, and then there are 4 columns. So there's 4 columns. Now what I want you to imagine is just this column here. Let's analyze this one. If you look at the column, it's circular, cross section, but when you look at it, it's hollow. So because it's hollow, it looks like this, like a donut. Not a donut, it looks like a ring. If you want to look, the best word probably to use, it looks like a washer. So the area of this column, I don't know why it's hollow. Maybe it's just cheaper that way. But there's advantages for it to be hollow, which we're not getting into bending strength or anything here. But if you're going to have a certain amount of material, if you make the column hollow, it's actually more resistance to bending because of its moment of inertia. We're not doing that calculation here anyway, but we need the area of this column. So when you look at it, there's an inner radius, and then there's an outer radius. So that's what Ri and Ro are, the inner and outer radii. So we can find the area of that column by just doing some simple area calculation. I've done it here already. Don't worry, I'll clean this up. So there's the calculation for the area of the cross section. I did pi r squared minus pi r squared with the associated, the appropriate subscripts here of the outer and the inner radii, respectively. Notice the units are in centimeters, but we anticipate that we're calculating something involving a stress. So then we need to convert that to millimeters if we're dealing with the metric system. So we would do that, and of course you can punch this all in your calculator and get approximately 8,473 square millimeters. Any questions about that calculation or about the design or the diagram here? Okay, so this object, this structure, I should say, it has this thing here in yellow, this object is 5,100 kilograms. But we're saying that each column will equally share that mass or support that mass. So that means that the force in one of these columns, so if we go here and just call this here F, that's F there, then F is going to equal the weight of this object here divided by 4. So here's the calculation for that. It looks like a lot of writing, but just read it carefully. It's nothing too bad. Nothing too dangerous here. The total mass is 51,000 kilograms. And then the total force, or if you want the weight of the structure, you remember we talked about multiplying by 9.81. So that takes us to 500,000, approximately 500,000 newtons. And then our force, F, is going to be the total force divided by 4. So approximately 125,000 newtons. So now we're good to go, people. We have everything in the toolbox here. We got this, which is the area. Whoops. We have the area. We have the force. So all that remains is to plug that into our stress calculation, and that's it. So as Sean said it earlier, it's just more steps. It's just more steps. And I strongly believe that. Managing more steps and also being attentive to what the units are in the question. Yeah, that is definitely a standard conversion, yes. If you want to convert mass to weight in the metric system, we multiply by 9.81. This goes back to a previous unit, Anthony. So I'll just say it here. Kilograms to newtons. I have to type it in the formula mode. Kilograms to newtons in the metric system. I'm not trying to say it childishly. Like I did give you a very detailed explanation about that in a previous unit. But just for now to address that comment, that's just like the quick thing, okay? There was definitely more discussion as to why it's 9.81 and what it would be, for example, on a different planet or just floating in space. So it's 8:50 approximately. Let's take a break till 9 o'clock, or 9:05 actually. What is strain? Now that you know materials are subject to forces, and those forces are transmitted through the material as something called stress. When the material undergoes stress, it's going to change. It's going to change somehow, geometrically. So for example, under tension, if you have a wire or a cable or something, it's going to elongate. And if you have a column, for example, that is being compressed, it'll shorten. So think of it like a percentage change. You could have a positive or a negative change because you could extend or you can contract. That formula for that change, that relative change, is called strain. So here's the formula for strain. Okay? Strain is the relative change. So you see, when we say relative, relative means to some reference point or reference amount. In this case, the reference amount is the OG. It's the original length, okay? It's the original length. And delta L is the change in length. So for example, if it's now it says here calculate the strain, whatever. That was a typo. I've actually edited this out of the document, so you can ignore that. So my apologies for that. I've actually already corrected it on the solutions. So that's what I was saying, that you might find the odd typo in here. Anyway, an important point to make though is that strain is dimensionless, has no units. The reason it has no units is because you're dividing length by length, and those length units are consistent, then you should have no units in your answer. So typically, strain is expressed possibly as a percentage. I won't say it always is, but that's a common thing you'll see for strain, is that it's a fraction or a percentage. So let's take a look at an example here. I don't think that you'll particularly find this question, the next few questions, difficult, but that doesn't mean we're going to go fast through them. So we have here a rod that is subjected to a stress, and its tension, because it's pulling on it, it's going to elongate. And then we see that it elongates by 12.4 centimeters. So the question is, what is the strain? So let's do the calculation. So the Greek letter here is epsilon. That's the Greek letter for strain. You can just write the letter E if you're lazy, but I like to use the right letter. So in this case, it elongated by 12.4 centimeters, whereas its original length is 352 centimeters. Can someone confirm the answer here? Did you get this? Please confirm in the chat. So, thank you. So I mentioned at the beginning of class, there's really three formulas you need to know today. The first one was the stress formula, which was intense. I started you off with a nice intense formula. The second formula you need to know is this one, which is relatively easy. You're just dividing two lengths. So you see what I'm trying to do is kind of balance it out. And then the last formula will be a tough one as well. and tougher one, I should say, than this. And that's basically the class. So, are there any questions about this, or shall we move on to the next one? There's only 3 questions to do from strain. They're very short and sweet. Materials will also change their shape for other reasons. One very common one for metals is thermal expansion. And I'm sure that in another course like building science, your professor will cover something like thermal expansion. Or possibly in the materials course. I'll talk about it right now, Jai. Sorry. So it says here that we have an initial length of that, and the tension gives us a strain of that. What is the final length of the wire? So I'm just going to write the formula, and I'm going to see what we can do with this together. So we have here strain is equal to delta L over L. The strain is 3.4%. So you can put a percent, but you're better off making it a decimal. The original length is 13.4. You see what I did as the strain was represented as a percentage, but I immediately wrote it as a decimal expanded. So no percent, to answer Jai's comment or question there. Now we just solve for the change in L. You're very welcome. So just cross multiply that stuff, and you're going to get 0.46 meters. I rounded this to, I rounded it as such because the question says the nearest centimeter. So this is not centimeters, but you can see that 0.46 meters is rounded to the nearest centimeter because it's to the 100th of a meter. Now that we're there, we're good to go. Final length, here we go. Final length of the wire, I can spell. That's going to be equal to L plus delta L, which in this case is 13.40 plus 0.46, which is 1386. Just some decorative touches here, and then we're good to go, my friends. What do you think? What do you think about strain? Is strain easy? It's easy. It's kind of funny because you hear words like stress and strain, and in everyday life, when you use those words, there's some assumption, or it implies somehow that it's like it's a burden on you. Like, I'm stressed out today. And the irony is stress for physics calculations and strain even for physics calculations, they're not that bad. Yeah, you got to know some area formulas here and there, and you need to know your bed mass. But heck, you've done integral calculus with me. You've done antiderivatives. Going from antiderivatives to bed mass should be a bit of a downgrade in terms of how much effort you need. Anyway, let's go to number 11 here, which is just one more question involving strain. So it says here a wire elongates by 2.5%. If the change was 1.7, what is the original length of the wire? Ooh, okay, so this question is easy peasy. Easy peasy. Because we have this formula here, which is the OG formula, and we're just going to rewrite it. So if you want to solve for L, what does L equal? Solve for L in the chat. What do you got? What does L equal? What does the original length equal in terms of the strain and the change in length? It's funny, by the end of this course, by the end of the year, you have your math prof here who is speaks Greek fluently and is even qualified to teach it. You're learning the Greek alphabet with me. So it's like you're not even learning, you learn 2 math courses and the introduction to the Greek alphabet. So go figure that. So there you go. I just did the calculation here from the solutions, if you don't mind. Save myself a little bit of scribbling on the PowerPoint here. So just take a minute there and look over that answer, make sure everything's cool. We'll resume in a second. I'm just in 1 minute, sorry. I just want to go back and just check something on my own. Okay, so where are we now in terms of the physics? I've talked to you about how it's important to understand the concept of stress because stress tells you how a force is distributed through a material. I've also talked to you about strain, where strain refers to the percentage, if you want, or the relative change in length of the material. But the one thing I haven't mentioned yet is the material itself. So for example, in any of the questions that I mentioned, if it was copper or iron or concrete or any of that stuff, not a single question did it really matter. I think one question said mild steel, but it didn't even matter that it was mild steel. The one with the wire, I think, or the column. Anyway, the point is that now we want to connect things together to create the super equation, the one that really ties together all the physics for this booklet and is very just immensely important in design. And it's this equation here. This equation here. This is such a powerful equation. So let's talk about what that means. Stress is just what we know as force per unit area. Strain, epsilon, is how the material is going to adjust or stretch or compress, like the geometric response to the material. And then E, that's the big one. E is this special quantity called Young's modulus, and it depends on the material. So depending on the material, the stress that you apply will have a response in the material of elongation or contraction. And then this formula tells you precisely how much elongation or contraction will occur for a given material under a certain amount of stress. So this equation here, it ties everything together into one harmonious single equation. Let's talk about the units. What are the units for this? What are the units for E? For strain, sorry, epsilon. Nothing. That's right. Strain has no units. See? Strain has no units. So that means that the units for stress and for that value E, which I'll discuss in a second, they're equivalent. So I want to say it again. This quantity E depends on the material. And that quantity is called Young's modulus. So if you go to the next page, when you have these notes available on Blackboard, I'm not going to ask you to regurgitate a bunch of materials, but I'm just talking about this right here. I'm going to put a box on this because we're going to refer to it today for a little bit. We have aluminum, copper, iron, concrete, and then a certain type of steel, which is 1020 steel. And you can see here that the Young's modulus value for each of these is given in the metric system in gigapascals and also in pounds per square inch in the imperial system. So in a practical sense, when you're doing questions, you would need to either look these up online or in a manual or in some type of a reference. For us, you can just pretend that this is your engineer's manual and you just have these here handy and you're like, okay, I'm dealing with copper, no problem. There's the stuff I need to know about copper. So we're going to go through some questions together and then it should be pretty much wrapping up in terms of the theories and then after that we'll do a few design questions to finish off the class today. So firstly, let's just talk about the formula here. So for the metric system, stress, we already mentioned, is megapascals, and in the imperial system, it's PSI. Although the quantities are quoted in gigapascals that I showed you earlier, that's just because those materials have a very high value for E, which is called stiffness. Young's modulus, another name for it is stiffness. So the larger the Young's modulus, the more stiff it is, meaning the more resistance it has to stretching out. The units for the Young's modulus can be megapascals or gigapascals, typically, but I want to use the same units here so that you remember that they are supposed to be consistent. And strain has no units, as mentioned before. We can also solve for various quantities here. So we could have here the Young's modulus would be the stress divided by the strain. And then you can also have here the strain, which is the stress divided by the Young's modulus. And don't worry, people, this is the last real formula that you need to know today. There's a couple of little nuances that are just more design oriented, but this is the toughest part of today's class. So here's the first question. It says a material undergoes a stress of 141 megapascals and experiences a strain of 3.1%. Determine the Young's modulus for the material. Don't worry about the gigapascals right away. Just worry about Young's modulus. Start by writing down the formula. So there's the formula. And then we can do some substitution here. We know the stress is 141 megapascals. Young's modulus is unknown, and strain is 031, like that. Any questions about this calculation? Are you kind of okay with it? Who feels okay with what I'm showing you? Okay. Anybody else? Anybody else okay with what I have so far? Thank you, Ravi. I got 25 other students in this class. I got 25 students here, so hopefully I can hear from some other people as well. Thank you, Gianluca. Thank you, Joshua. Thank you, Amir. Okay, so in this case, like I said, these are my first time delivering these ones, so double check the calculation with me. Anybody else get 45, 48? Can someone confirm that number? And then let's convert that to the gigapascals. So there's the answer when you divide by 1,000. So 4.55 gigapascals. Now this quantity here, E, which is Young's modulus, you could go back and like a detective, you could figure out which material this is. So it's kind of like a DNA thing. Like you can go back and find out which material it is and then identify it. Or you can also, in a design perspective, say, well, I need a material that's at least that. We're going to talk about the design aspect after we do some more of these questions, these are questions that are just basically manipulating this formula. So let's just keep on going on that note here. Okay, so this next question, an iron bar experiences a stress, and then it says determine the strain in the bar. Iron, wait a second. What's the Young's modulus for iron? Now, some of you probably don't have the booklet in front of you. I respect that. So if you go back and look for iron, let's go for iron. Yeah, G, you meant G there, Jai, right? Okay. So I'm gonna go back to the table because some people, it's okay. Thank you. So let's go back here. Here's iron. See, 211 GPA, but there's also PSI. So why did Jai pick the GPA one? Why did Jai pick gigapascals? Because the question was in the metric system. If you go back to the question, it was megapascals. So that's a metric quantity. So let me just say here from the table, let me just put a subscript there. Maybe that's easier. There we go. So then we have the stress. So you see that there's a little bit of a discrepancy between the two units. We'll deal with that shortly. Let's convert them both to megapascal or both to gigapascal. It doesn't matter which way, as long as you make them the same. So there, I just decided to go with megapascal because strain should have no units to it. So if you calculate that, if you evaluate that on your calculator, sorry, that's what I got, which is as a percentage is that. All right, I think we're going to move on to the next one. Got a copper wire. Basically, question 15 is the same as 14. The units are different. That's all. We're going from a metric situation to an imperial situation. I'm just going to recycle a lot of this here. So there's kind of the skeleton of the question. So we have the stress. The stress is given. It's 65,200 psi. But we don't know what the Young's modulus is for copper. So go back here to copper on page 3. Copper, we have two numbers. We have 130 gigapascals, and then we have a number that's in psi. You want to use the number in psi because the question is in psi. It's in the imperial system. So that's 1.89 times 10 to the 7, or roughly 18 million. 19 million, sorry. So let's go over here and fill that in. So there's the number there, 1.89 times 10 to the 7 psi, which we can just toss that in there. Then E equals 65, sorry, Young's modulus is that. So then the strain is equal to 65,200 divided by the Young's modulus for copper, which is approximately 0.00345 or 0.345%. Can someone confirm that number there when they're ready? Thank you, Sean. Let me know in the chat, people. I know there's a lot of us here, but some people are not really talking too much. Let me know if you need me to slow down. I definitely won't go faster than what I'm going, but please let me know if you need me to slow down. On the bright side, there really is only two key formulas, and the strain one really is not that much of a big deal. It's really the first one that we did and the one that we're currently using that form kind of the lion's share of the effort that you need to use to solve a question. Strain calculations are easy in terms of relative length. So we can proceed to question 16. I'm going to go there now here. So we have another question involving a stress calculation. In this case, we have aluminum. Now, if I look up aluminum on the table, I did that earlier, and I got 70 gigapascal. The question is to find the stress. So the good news is that we already have the quantities and the formulas in the orientation that we want. But we just have to convert the strain into a decimal. So that's the original as a percent, but remember to go to a decimal, you add 2 zeros to the decimal, and you can multiply that out. The other thing is the question wants it in megapascals. So perhaps I might be better if I just do the extra step here, where I just actually show that expansion. So I'll call that 70,000 megapascals, and then 0.0021 units of strain, sorry, amount of strain. So that should finish off this question nice and clean. Can someone confirm 14.7, please? Actually, that one's easy to do in your head. It's okay. Never mind. So there you have it. So we're getting there. We're getting to the place where we can do a few questions that are really like serious application questions, reminding you or at least giving you the hint of what people do in real life, not just like this fairy tale world that we live in called first year mathematics, first year degree mathematics and physics. So this next question is going to be the question that is we're on the precipice of that big jump. Okay, here we go. So this question really ties a lot of the stuff that we did together, literally. I think that sounded grammatically correct. Anyway, we have a column that experiences a compressive force. The cross section of the column has an area of 42.3 square millimeters. We are told how long the column elongates. It only elongated about 3 centimeters. Now, for a 4-meter column to elongate 3 centimeters under a load, it's probably a little bit too much, but that's fine. This question is just more about practicing the formulas, and we definitely will consider what design aspects you can consider. Sorry, we can consider design aspects after this example. So for now, just execute it as a math question. It says here, determine the Young's modulus of the bar. So we're trying to find the value of E. So I'll start by writing the formula. So in other words, we need stress, and we need the elongation or the strain, and then we can get the Young's modulus. That's kind of the game here that we're playing. So it's tic-tac-toe, 3 steps, people. So let's get those 3 steps on paper, and then we're good to go for this question. So start with the stress here. Can someone in the class explain in the chat how you would calculate the stress here? What would be the stress? Ravi, that is correct. So what Ravi did there, to clarify, is force divided by area. And notice that also Ravi expanded. We had 21 kilonewtons. And I'll just do the numerator first. The 21 kilonewtons became 21,000 newtons. The area is safe. It's just millimeters squared, so we don't have to play with that. It's easy. Doing that earlier, I got 496.45 megapascal. The strain, now this one's under compression. This one is under compression. So technically you should have a negative answer here, but when I present it as a positive quantity. So it's a bit lazy on my part, but you can definitely interpret it or should present it if you want as negative. I'm not going to pick on you for a negative or a positive here. So I'm just going to leave it as a positive, even though it's compression. Actually, no, it's supposed to be contracts. So there is a typo in the question. I'll have to make this correction later. This should be tensile. That's a typo in the question. So I retract what I just said there. I'll fix that mistake later in the notes because it's an elongation, so that should be tensile. So my apologies for that. That's why I was getting a little confused for a second there. I was like, what the heck? Why is it expanding but contracting? Anyway, in this case, the elongation, I'll make that correction at the end of class and I'll re-upload the booklet. So my apologies for that typo. The original length is 4.21, sorry, meters. That was a little bit embarrassing. That's okay. Anyway, one of the strange things about being online and teaching online is, for me, I like when I make notes and I make reports and such, I have a colleague or a friend in the office that they'll kind of will bounce ideas off each other. But it's really hard when you write notes by yourself and you don't have someone that can help you proofread them. So I realize that's probably one of the shortfalls for me in terms of how I do things as a professor, or even back in the day as a student. If you're in an isolated situation, it's very hard to get feedback. But anyway, it is what it is. So like when you're working on your assignments, it's obviously your assignments should be independent study. But you know, if you're doing math and you're trying to help each other, I'm not going to pick on anybody if, like, you know, if Sean asks Ravi, you know, what units are good or whatever, vice versa. I'm not going to go, oh, Sean, you cheated or something. No, that's not what's happening. I understand that you have to help each other to figure out little things like that. But anyway, back to the question here. We have the big thing. So you see how the first part of the answer, you have what we did at the beginning of class, and then the second part of the answer is basically what we did just at the second hour, starting at 9:05. And now we're going to tie it all together with our new formula to figure out what the Young's modulus is for this material. So in this case, let me just toss in some numbers. Notice that the units are going to be also in megapascals. As I mentioned, that stress and Young's modulus have consistent units. Sorry, that's 72,100. But the question says to write it in gigapascals, 3 sig figs. So that's why you see there I put zeros to the nearest hundreds. Nearest hundred, I should say, because of the aforementioned 3 significant digits. So there's the answer to the question. This material, whatever it is it has a Young's modulus of 72.1 gigapascals. So very stiff, a very stiff material. Usually when you see Young's moduli, plural for modulus is moduli. When you see Young moduli that are in the gigapascal range, they are definitely super stiff materials. So it's 9:47. We are going to do 3 more questions that are in the design aspect. So what I'd like you to do, I'm going to give you a break till 10. but it's going to be a thinking break, so maybe not really a break. I want you to just read. I'll leave it on the screen here for you to read. It's just very, very cheap. It's this, okay? Safety and design. So I'm just going to leave this on the screen, but I'll just put this here first, make sure everybody's got the answer down. Once everybody in the chat here clears us from looking at this again, I'll go back and ask you to just read over that little text where I talk about factor of safety. The basic idea in terms of safety is that although a material can handle a certain amount of stress, we don't want to push the material to its limit. Because in design, if you were to go to the limit of the material, you're gambling. And you want to introduce something called a factor of safety so that you never really get into that realm. And that factor of safety should be many multiples of whatever the, many fractions of whatever the yield or ultimate strength is for that material. And I'll discuss what this yield or ultimate stress is in a second. So we go back here, there's a couple of graphs that I skipped over earlier, and they just discuss what happens when a material is undergoing stress. The key part that I want to talk about here, we'll discuss this graph here, which is for a material under tension. This is what happens. When you apply a stress to material, it's going to elongate, creating what's called a strain. The idea is that when you release the stress, the material should also release its strain, meaning it should go back to its original length. So that's what you have here. As you put stress on the material, maybe up to here, if you let go of the stress, it should go back to its original state. And materials have what's called an elastic limit. That elastic limit is the limit of stress that you could apply to the material that when you release the stress, it, so to speak, quote unquote, bounces back to its original state. So the elastic limit right here is the amount of stress that you're allowed. That's this first value that you could have before you can bounce back to your original state. Then you have something called the ultimate stress. That's the amount of stress that you could take a material to before, after which it will fail. There's also one more thing called the yield stress, and the yield stress refers to the amount of stress that you can have that if you release it, it goes back. Because there's two regions here. There's a straight line region, and then there's a curved region here. Those regions collectively represent a limit, an elastic region. So after this point here, if you were to undergo certain stress, the material would have a permanent deformation. It would literally change. The example that I can give you, and I'd love to show you a demonstration of this, but I'll probably injure myself, knowing me, is to take an elastic band and to hang masses off of it. So when you take an elastic band and you pull on it, if you don't pull a lot and you let go, it goes back to its original state. So that would be in the elastic region. But if you take an elastic band, and I know many of you have tried this, I want you to imagine pulling on an elastic, but if you do it slowly enough, do you know what happens to the elastic? Have you ever tried that? You might notice that it starts to change color. It maybe smells a little bit differently. It permanently is changed. And when you let go of it, it doesn't bounce back anymore. So that's what's called plastic deformation, or meaning that you've permanently deformed the material. Bottom line is that in design, there are these yield and ultimate stress values, which are quoted based on research on the material, and then a factor of safety is used for you to limit how much of the strength of the material you want to exploit. So for example here, let's say you have aluminum. See aluminum here? Aluminum has a ultimate strength or ultimate stress, if you want, of 45 megapascals. If I use a factor of safety of 9, that means I just chose 9 for arbitrary reasons. A factor of safety of 9 means that I should not go more than 5 megapascals. Although the material could handle 45, I'm not going to push it to 45. I'm only going to use 5 of it, even though I know it could handle as much as 45. That's what safety is. That's what it's all about. So there's a show I watched. I don't know if it's on TV that much anymore. Who's ever watched Mike Holmes? You know Mike Holmes, the renovator? Mike Holmes. Okay. So the fun part about Mike Holmes is that I watch his show, and as an engineer myself, it's funny because he loves using really large factors of safety, like really large. So it's very fun to watch because when he builds stuff, I'm sure that it costs a bit more, but when he builds it, that thing is built to last. I'm not a salesman for the show. I'm a little bit of a fan of his because I think he's entertaining, and also it's a neat show to learn about some of the mishaps that people go through when it comes to design and renovation. Anyway, let's take a look here. Three more questions to go. Nothing too dangerous. So let's see what we have here. Determine the maximum allowable stress of a concrete column if the factor of safety is 8. Okay? So this question is not hard because all you're doing is accessing the number off the table. So it says here it's in PSI and it's concrete. So go back here and look for concrete. Here's concrete and it's PSI. So it's this one. Does that make sense? Let me know in the chat. Concrete ultimate. Just reading a number off the table. Cool. So we go over here. Sometimes the factor of safety is based on the yield, sometimes on the ultimate. You do not have to decide that for this course. It would be told to you. So you're not a psychic. Nobody's asking you to design anything out of thin air. You'll be carefully guided in terms of what I ask you in questions. So I just looked it up on the table. There's the number that we circled, 5,800 psi. We know the factor of safety is quoted as 8. So you take those numbers and divide them, and you get 725 psi. So all we've done here is given you more guidance on how you actually use the value of the ultimate stress for a given material. So where do these factors of safety come from? For those of you, you've taken building code. Who's taken building code? You should have taken building code at some point, right? Okay. So we're doing it this semester. Gotcha. I couldn't remember if it was first semester or this semester, but I know it's a first year course. In building code, I'm pretty sure that in the OBC that there's definitely mentions of factors of safety for particular design considerations. Correct me if I'm wrong, but I'm pretty sure that in building codes that there are factors of safety that are quoted. So we have two questions left, and they both involve design. And by design, I mean we're invoking factors of safety. So we're really trying to push the limit in terms of showing you practical questions. So we're going to do two questions. They might take us 20 minutes. They might take us 30 minutes. I don't know. We'll just go nice and slow and make sure that we get the most out of this experience together. So here we go. We have a copper cable. And I was mentioning at the beginning of class that I said by the end of class, you could be able to take a copper cable out of your toolbox or shed or whatever, garage or whatever, and be able to very carefully and with very decent mathematics, good accuracy, predict how much of it, how much you could lift with it. In this case, it's more of an inverse problem. I'm telling you what the load is or the force, and I'm asking you to find out what the minimum diameter would be for this wire to be safe. So it's kind of the inverse question, but still a comparable question. So the question is, what is the diameter required for the wire to be safe? And we're going to be doing a stress calculation. So we're going back to the stress stuff that we did earlier. So this question actually falls in line with what we did at the beginning of class today, except we're introducing factor of safety and the material characteristic. So ultimate stress, copper, and metric. Those are the keywords. Those are the keywords that I'm using to figure this question out. So go back to the table on the third page. Ultimate stress, here it is, copper, metric. So 210 megapascal. For your assignments, I'm sure you'll have a question that relates to this stuff. Make sure you use the numbers in the table that are given in these notes. Please do not do internet searches for any numbers because it'll kind of mess up my marking rubric. So I'll make a note of that in the assignment. Make sure to use the booklet to find any numbers that you need, including ultimate or yield or Young's moduli. So in this case, we have ultimate stress is 210 megapascal. We now have to consider factor of safety of 8. So like the previous question, we take the ultimate value and we divide by the factor of safety, FOS. So in this case, it's 8. So that's 8 there. 210 divided by 8 is 26 and a quarter. Okay, up to this point, let me know in the chat. Did this make sense right now, what I did? Let me know in the chat if this made sense. Thank you, Sean. Let me see some more people here. Let me see some people so I know that I have a nice representation of the class here. Nikita, thank you. Thank you, James. I'm not saying thank you to everybody. I feel bad, but I appreciate all your comments. Okay, well, good news, my friends, because the rest of the question is reminiscent of what we did earlier in the first hour. Remember that last question in the first hour that we had the radius, and we got the radius or whatever, the diameter? Very similar question to that. So we're going to get the force. So the force is equal to 2.12 kilonewtons, which thousands, right? So that's 2120 newtons. And then the area is equal to the force over the stress. So that's going to be, in this case, 21. I encourage you, if you want to see more of these types of questions, these last ones that I'm doing, in the other course, I'm posting videos on Blackboard. In that other math course, I mentioned to you during the previous break, I highly encourage you to watch those lessons. I'm starting those lessons on Friday for that course. So if you want to see extra practice and a bit more theoretical perspective on stress and such, design considerations, definitely check out that video or those videos. I didn't capitalize the P there. Okay, so area. What are the units here? What are the units going to be? Who remembers what units I'll have here? Very good, Sean. Very good, Sean. So that's millimeter squared. We're almost there. We need the diameter. So we got to get that radius now based on the area. So I did this calculation. Whoops. We don't. Let's get that back there. Damn, almost lost the whole question. I'll go to my solutions for this because some people ask me in class, why do you get the radius when there's a perfectly good formula for the area of a circle in terms of its diameter? Why bother finding the radius at all? And I agree with those students. You don't need to find the radius if you're being asked for a diameter. So here's that permutation of the question. I'll just kind of maybe just increase it a little bit here so it looks nice. So what I did is I wrote down the area of a circle because it is a circular cross section, and I did pi d squared over 4. So then I resolved for d here, and you can do algebra on your own for that. That's not too big of a deal. Anyway, the thing I want to point out is that when you do all this work on your calculator, you get this. You get 10.140 millimeters. Going to the question, you'll see that it's minimum diameter in millimeters. You see that there? And also 3 significant digits. So I need to know if the answer is 10.1 or 10.2. So the debate here is really, is it 10.1 or 10.2? In mathematics and in science disciplines, when you see the word minimum of something, you should always round up. Should always round up. Because if you do 10.1, it's not enough. You have to round up. Does that make sense, rounding up? Okay. I'm going to clarify with a really, really silly example. Okay? Here's my example. Now, for many of you, I'm probably much older than most people here. I'm not saying we're not talking about how old everybody is here, but I'm in my 40s. So back when I was in high school, the bus cost $2.25. That was the bus fare. So I'd hop on the bus and I'd have a toonie and a quarter. Now imagine I was acting like a mathematician on the bus. Could I do this to the bus driver and say, look, I'm rounding to the nearest dollar, and just give the bus driver $2? Would the bus driver let me on the bus? Yes or no? With $2? Well, maybe if they're a nice person, they'll let me on the bus, but the answer is no, because the minimum fare is $2.25. If I want to round it, I have to round it up. So if I only have dollars on me, like loonies on me, unfortunately I got to toss a $3 bill in there, $3 in there. You see what I mean? Thank you, Abdullah. Because you got to round it up. It sucks, and I'm sure anybody here who's been on a bus before, they know when you don't have enough change, or when you know what I'm saying, when you don't have exact change, you have to round up. Too bad, so sad, right? It sucks. It's happened to me a few times. Going on the bus, and it's like the bus fare or whatever it was, or the subway station or whatever the heck it was $3 or $2.50 or whatever it was, I forget. And I'd have a $5 bill. Too bad. Throw a $5 bill in there. Anyway, enough of talking about the bus. I'm sure everybody has had their fun times on a bus before. So let's move on and do another question involving real life calculations. Turn you into engineers. From construction managers, you're turning into engineers today. How do you feel? You're getting a taste of what I had in first year. You are little engineering disciples now. Here we go. Last question for today. I had a course in my first year in the fall semester, which was basically this and some more stuff as well. But it was really fun to do it because I started to look at the world differently in terms of like design and optimization, and really thinking about, like it says here, taking into consideration things that are meaningful, like safety, not just like, oh, I do some calculations and who cares. Like, you actually have to think about how it impacts the world around you. So, enough philosophy. Let's do a math question and call it a day, my friends. We have here a steel cable, and the diameter is 2.84 centimeters. I mentioned it here just in parenthesis, not more than an inch, not much more than an inch, because an inch, as you know, is 2.54 centimeters approximately. So imagine that you pull a steel cable that's not much more than an inch. Maybe you find it on a job site or just leftover in a construction project. And then you're like, you know what? I want to know what the maximum mass that it can support is. But because you don't want to injure yourself, you introduce a factor of safety of 6. Now, again, you don't have to be a psychic, and you're not a building code expert in this course, but you should know your building code for your course and your program. I'm just going to say that the factor of safety here is a 6. So anyway, it says here, what is the maximum force that the cable can withstand and the maximum mass that the kilograms that it can withstand or support? And of course, presentation, significant digits, etc. So let's take a look here and see what the heck's going on. So it's a steel cable. So the first thing you want to do is look up what the steel cable is. Now I'm gonna just give you the answer for that because we can look it up in the table later. Oops. You know what's funny? I should mention this here. You know this Greek letter is the letter sigma. I've been saying it today in class. So the lowercase of sigma is this. The uppercase of sigma is this. So now you know both the lowercase and the uppercase of this Greek letter. So look at that. And the Greek alphabet is 24 letters. So now you learned fully one more letter in the Greek alphabet. So look at you. Becoming multilingual if you aren't already. So we have the ultimate stress, which is 420 megapascals. And then we have our design stress, which is the stress we want to use. And that'll be the ultimate divided by a factor of safety, which in this case is 6. So what is our design stress? In this case, it's 420 divided by 6, 7,642. So that's a nice little mental math question. So we can do that. How are you guys doing? How's everybody feeling here with this stuff? You feeling like you're doing something meaningful, something new, something dangerous? What do we do next? Let me know in the chat. What should we do next? Any thoughts? That's the formula we're going to use eventually. But let me know in the chat. What do we do next? We're trying to calculate the force. See that? We're trying to calculate the force here. So if we're trying to calculate the force here and the mass as well, then we should find out what the area is, because the area is the next thing. So in this case, the cable is a circle in cross section. So the cross-sectional area is the area of a circle. The radius is equal to, ooh, this is dangerous. We don't have the radius. We have the diameter. The diameter is 2.84 centimeters, which is 28.4 millimeters. That means the radius is equal to half of that, 14.2 millimeters. Confirm? Someone confirm these numbers? Anybody? Thank you. So we get that out of the way there. And we get 633 approximately square millimeters. At that point, you're good to go. You can rearrange this formula and say that force is equal to stress times area. So we know the stress, which is 70 megapascals, and the area is this number here. Quantity here, I should say. Okay, so after doing a little bit of work here, we get 44,343 newtons, or that is 44.3 kilonewtons. That answers part of the question. That's one of the questions. It's asking for the force in kilonewtons. So we got that out of the way. And then the last part of the question, it goes back to what I mentioned earlier. So I'm just going to recycle something that, if you remember, one of our classmates here asked this, kilograms to newtons, that conversion. So I'm just going to go back there and steal that for a second. So we can finish off the question now and say that the kilograms, or the mass, is equal to 44,343 newtons divided by 9.81, and that's going to be approximately 4520 kilograms. So that's the end of the question. Now, I mentioned earlier that 9.81 does have units here, so I will put the units here. It's meters per second squared. You can also say it's, if you prefer, another units for that quantity. You can also say newtons per kilogram. These two things are the same. I'm just going to highlight this in gray so that you don't think, I don't want you to think you have to write them both or something. Whoops. Because only one of them is needed. The units are equivalent, so that's why I'm just graying that out. Okay, so that's all of it. I'll stop recording now and just discuss any questions that you might have regarding the course, the material, and this lesson. So thank you.